Hi guys, and welcome to week 2 of lectures. I am Dr. Elizabeth Kiriakou, and today we're going to take a look at frictional forces. So up until now we've looked at equilibrium, we looked at our equations for equilibrium, so the sum of the forces on a system needs to equal 0 and the sum of the moments need to equal 0. We've taken a look at our reaction forces, and now what we need to do is we need to add friction to these problems. So what is friction? So friction exists between two rough surfaces. So if I have a box here, and I've just exaggerated the distance between the two a little there so we can see, and I have a force pulling my box in this direction. Okay. So friction opposes the direction of motion. So friction opposes the direction of motion. So if our force is moving in this direction, this way, which way does our frictional force go? Friction will occur at the contact surface, and it's going to go in the opposite direction to the force. So this is my friction force. Okay, so what other forces do we have acting on this box? We're going to have, at the centre of the box, a weight force, which is mg. So we know that m is the mass. So m is the mass, and g is the gravitational force, which is 9.81 metres per second squared. And are there any other forces acting on this system? There's one more, and that is our normal force. That's our normal force. And this is always perpendicular to the surface. Perpendicular to the surface. So now we have all the forces added on. Let's see if we can actually calculate or write an expression for a frictional force. So friction equals mu s times n. So mu s is our coefficient of friction, and this has no units, and n is, over here, our normal force. So if we want to find the frictional force, we need to actually resolve our forces in the sum of the forces in the x and the y direction. We can find what our normal force is, and therefore we can find what our frictional force is. So let's take a look at another case. What happens if we have a box now on an inclined plane? Let's clean this up. Okay, so let's take friction on an inclined plane. So here is our plane, and we have an angle, our plane is at an angle theta. And we're going to draw our box in here. And this is the centre of our box. So I'm just going to draw an axis up here of x and y. So So the box wants to slide down the plane, right? So that means the force is going to go this way. So sliding down the plane. So what are we going to have? We will still have mg, our weight force, but now our frictional force is going to go up the plane. So here is my frictional force. And we're going to have one more force left over, and that's going to be my normal force. And that is acting perpendicular to the surface. So normally we would solve the question with our original coordinate system. But to solve this simpler, what we're going to do is we're going to rotate the axis and then split it up into its x and its y components. So then my axis is actually going to look like this, x and y. So my pulling force P is in the x-plane, the frictional force is in the x-plane, N is in the normal, is our normal force, and that's in the y direction. And the only thing we need to break up into x and y components is our mg. So we will have mg in two directions. So this is what we'll have. Theta here, and this side will be mg cos theta, and over here we will have mg sin theta. Okay? So this is, to solve these problems, we're going to rotate the axes to match the inclined plane. So I can say that this way is positive x now. So sum of the forces in the x direction has to equal 0. Let me change colour here. And we're going to have P is positive, friction is Ff, and we also have mg sin theta. So how else can we express F? F is also going to equal mu n. Yep. And then I can also say sum of the forces in the y direction has to equal 0. So I'm going to have my normal force n, which is positive. mg of the y component is going to be negative. And that's all I have. So we can actually calculate any component of this diagram using some of the forces in the x direction. So if we use our equations for equilibrium, we can solve anything. So some of the forces in the x has to equal 0, and some of the forces in the y has to equal 0. And we just make sure that we rotate our axes. Okay.